Well, hello everyone. My name is Victor. I come from Ben Gurion University, where I'm in the middle of my PhD studies with Professor Bracha Shapira and Professor Leo Rokach. I'm very happy to be here today with such a big audience, and I really hope to convince you that nowadays we can easily develop a multi-class classification algorithm with Spark on really big datasets. So what we are going to do today is to speak about what Spark is, what Hadoop is, really briefly, not a deep dive. Then we'll see several algorithms which work or does not work well or perform well on Spark and Hadoop in general, and explain why. We'll see an example of a real data set with the code snippets. All the code is available at my GitHub repository, so you can go and enjoy yourself after the lecture. And I'll share some experience from the past years of using Hadoop in real production information systems. So let me just ask you how many of you are familiar with Hadoop, with MapReduce concept? Okay, so about half of the audience. So let me just briefly explain what it is. So it will put us all on the same page. Well, probably the best example to explain. Well, imagine that you have a lot of data, you have bread, you have different vegetables, tomatoes, onions, and every node, every computer on the left side stores its own chunk of data. And your mission is to prepare a sandwich on your way to work. So you can ask for every worker, every node, to slice its own chunk of data. And the chunks are absolutely different. They are not shared. And this is the map operation, which is followed by a reduce operation, which combines all the sliced chunks into one great sandwich. So this is what is basically happens in the behind the scenes in Hadoop and in Spark. So before we go into Spark, let's see what Hadoop basically is. Well, Hadoop have several nodes which have lots of chunks of data. And when you build the data, by building, I mean you train a model. You have to, many times you need to pass over the data again and again and again in an iteration of training and in the process of adaptive updating of the weights of your model, or when you need to train your parameters. So what is happening is that between every iterations, all the data is read from the disk, some computation is performed, the data is written back to the disk, then it is read again, it's written again, read again, and there are lots of read and write operations on the hard disk, which is actually very inefficient and costly. So these things work really slow. So in response to this slow paradigm, the Spark came out. And the most central concept in Spark is the RDD, which is a resilient distributed data set. So in contrast to Hadoop, what happens in Spark is that this data operates in very smart cache system. So the data is cached. If you perform some operation and you have an intermediate results, it is not written back immediately to the disk. And between the iterations of the training, the data is kept inside the memory. And this results in a really magnificent speed up, which sometimes is even order of magnitude. Okay, some more benefits about Spark. Well, it operates in a graph computation way. So those of you who are familiar with TensorFlow or DyNet way of thinking, when you compose functions one on top of another, and then ask them to be executed, that's exactly what is happening with Spark. And you have several languages you can use when you program. If you're really code ninja, you can go for Scala, which is the backend of Spark itself. All the immediate libraries arrive in Scala, only then in Java, which has the benefits of strongly typed language, and only later it arrives in Python. The machine learning library, which is the MLib, also supports the R language, which I absolutely hate. By the way, people who learn Scala, they say that there is a prize, entrance prize, to learn Scala, but once you learned it, it's really fantastic. From my experience, in most of the cases, Python is fine enough. Well, it's fine to program, it's very hard to maintain, like always. So let's just go to an example of a whole world program in Spark. Imagine we have a really big text file, which is it is so big, it is split on several nodes, on several hard disks, and we want to simply count each word, the number of occurrences for each word. So imagine you have a computation graph. First, you read the file, which is stored in this path, into some text variable, which is actually our RDD. I remind you, the resilient distributed dataset. I'll explain in a minute what it is exactly. And then you build your computation graph, which actually a list processing paradigm. Those of you who are familiar with Scheme or Lisp, this is exactly what is going on. And our output will be the following one. So we have a two-dimensional table, right? 2 columns, each word, how many times it appeared in a file. So let's go line by line and examine what is happening here. By the way, those are the RDDs. That is, text and counts are both, like, you can think of them as a handler to a file which actually is stored on multiple servers. And from a user programmer perspective of view, it's just a variable, very simple. And the thing about RDDs is that they are actually immutable lists, and the computation graphs on them are lazy. So you must call like compute when you are ready. So let's explain this, because it's quite complicated to understand at first glance. So imagine our text file contains the following line: Victor presents at PyData Meetup at Taboola offices at Ramat Gan. So at the minute I read this file into the text RDD, the file became actually a list. The list called text, and each element of the list is a line from the file. So we have a list with 2 lines. Well, for simplicity, let's assume that every part of a list is stored in another node inside our Hadoop cluster. Teach the first line here, and the second line here on the second node. Once I wrote text.flatMap and gave it this lambda expression, actually I declare a lazy computation which will split every element inside the list with a space. FlatMap, I remind you, allows for multiple outputs for every element. So the first element, this was his output with 5 elements, and the second element outputted this line. This is the FlatMap. Okay? In the minute we we wrote map lambda word 1, actually we go and perform the concatenation of 1 to every word inside this list, and we get this. So we have now a long list of pairs, where in each pair the key is the word, and the value is one that you just added, right? When you call reduce by key transformation, what you get is you get a combination by this key, and all the elements inside the list are combined according to the first element, and then processed with this lambda expression, which in our case just sums the value element of the pair. So we have 3 times the pair at and 1. So at the end of this process, we get A that appears 3 times. Well, just to convince you and to make you believe that it's very, very simple, let's see how it really works with the cluster for a minute. Well, that's something I prepared before. Okay. So what you see here now is a notebook in Databricks, where I just put the same code we just saw. Let me run it for a minute. Well, that's it. And how did I get the file here? I just got and drag and drop. It has some kind of upload mechanism. You can drag and drop a file here, so absolutely simple. What happened behind the scenes is just all the mechanism of distributing computation we just talked about. So I hope you believe me. So it's really, really simple. Tick, tick, tick. So, but we are about PyData here, right? So we are interested in machine learning and training and models. So what do we have to do with text? So let's go to datasets. So all the models and the trainings in Spark operate with the same kind of RDDs. And the elements that you should put inside the RDDs are of a type labeled point. Labeled point is a built-in type inside Spark, and it receives two parameters. The first one is the label, that is the class inside the training set, and the second is just the list of features. And each and every of the models and the algorithms we have receives this kind of list and the RDD. Well, I'll tell at the end of my presentation that there is some other mechanism of doing it for those of you who are SQL ninjas here, but I don't love it so much, but we'll talk about it 1 minute at the end. So something that is very interesting also, which algorithms can actually exploit the distributed structure of Spark. And the algorithms that really benefit from Spark are those who make as little as possible passes on the data. For example, naïve Bayes algorithm that can pass the data only once to count all the features on the data they need to converge and to compute its parameters, rather than algorithms that make many subsequential passes and reads of the data. So actually naïve Bayes or the clustering algorithms which can split the space of their data works really, really well and much, much faster than not on Spark. Random bagging, of course, because you can split both the instances themselves and you also can split the space of the features if you have two lots of them. And each subspace will be trained in its node. Random forest, probably my favorite algorithm when I don't use an RNN. So it's my personal choice to go to. I really, really love it. And of course, linear regression. And this is because Spark and Hadoop can multiply matrices really, really efficiently. So linear regression also works very well and very fast, even when you have datasets that are huge, terabytes of data, and not only lots of instances, but also lots of features. So if you have, I don't know, millions of features, it also works and scales, and that's the amazing thing about it. So which algorithms, we don't like them on Spark and on Hadoop? Well, neural nets, you have to do many passes over the data. You need to read the data again and again and again for each epoch. We don't like SVM, we don't like logistic regression and other boost for the same reasons, basically. Yes?
The neural nets, you each time just see some batch of the data, not the all data.
Well, actually, this is a little cheat. There are two extensions on Spark who do attempt to perform a neural nets implementation, which is distributed. They do split the space of the weights which are being trained, both in computation of the target and loss and both in backpropagation. But they do need to share a lot of information between the nodes to compute the backpropagation itself, so it's not that of a favorable algorithms, although you do have some benefit. You're right. So now let's get to some more complicated example, which is the PAMAP dataset. What is the PAMAP dataset? It's quite a big dataset, but it's small enough to run on the notebook that we get from a community. Community distribution of the Databricks. It's only 1.7 gigas. What we have here, we have 52 attributes. We do have missing values, and we do have a multi-class classification problem. What the problem is? The problem is, imagine you have a person with different variables. By variables, I mean it's called IMU, which is inertial measurements units, like they measure the heart rate, the temperature of the person, in which position the arm or the leg is, its acceleration, different features. And what we need to classify is what this person is doing currently. Is the person lying, sitting, running, speaking in front of amazing audience on PyData, ironing, driving a car, or playing football? And in this data set, we have 18 different activities that we need to classify a person for one of them. There are 10 subjects, 10 different people who volunteered for this task. And we have the data. So let's see how we actually do it. Well, first, just to get a feeling how this data looks like, when you open the CSV of the file of the data set, well, first you have the temperature, then you have the accelerometer, first you have the timestamp. We need to get rid of. Actually, some people say we don't, but I think we do. Then we have the class, the label. We have the heart rate, and the measurements of 3 different variables. And each variable consists of this 17 fields, which is the temperature, the acceleration, and pay attention, there are like 7 fields that the data, after it was collected, they concluded it is invalid and should not be used. So our mission here even more complicated. We need to get rid of some of the features. We need to complete the non-values which are missing, and we need to classify afterwards this huge data set, which is, by this point of time, is distributed among several nodes. Okay. So what we are going to do is first we'll read and clean the data. We'll leave only the relevant features that are valid. We'll compute the average of those features as our strategy for the missing values. You can also, for example, choose to fill with the most side effect computation, which we'll see in a minute how you can do it, because I remind you, these lists are immutable, and when you process them, you need to somehow, in a distributed way, to compute an average, and it's not that trivial. And then we'll finally train and evaluate the model, and we'll see how easy it is to just declare naive Bayes, random forest, and logistic regression with Spark. Sorry? Actually, logistic regression?
No, linear regression.
No, just a minute. Spark implements one versus all strategy for multi-class classification, so it actually trains number of classes minus 1 binary classifiers, which then compete one against the other, and okay, so on. So first, let's clean the data. Well, I remind you, we're starting to build our computation graph. First, we have the list of the lines. We come and we compose a function which slices the data, which splits it by a space, and then it removes all the indices that were declared invalid by the dataset provider. And the response, we get an expression, actually, which describes, once computed, the list only with the relevant features. Clear, right? Okay, so, but just a minute, I just thought, okay, what about side effects? Yes, what about average? What about mean? What do we want to do with it? How we can compute it once we can't really change and access the lists themselves, the RDDs? So there is a mechanism which is called an accumulator, which is a distributed counter. And you must operate in what is called a Hades, but let's tell it, associative and commutative way. That means the items you operate on can be switched in the order, and it doesn't matter how you group the items between the nodes. This is what associative and commutative means in this regard. So let's see an example. First, I'll declare a list of pairs where each pair is an accumulator initialized to 0. An accumulator can be accessed, like can be written only by a worker and can be read only by a master program, which is called the driver, which can access it after all the workers finished their update. So what is happening here is that I build the computation graph further, but now I call what is called in Spark an action, which is the computation graph is actually executed. It's not just declared as an expression, but the code is actually run. Well, what I have here is I just go over each line. If I see that the value there is not none, that is the value is not missing, we sum this feature and we also count it. What we want to do at the end, in the driver program, we want to access the value of these accumulators after they were summed and their counts and compute the average. As simple as that. And in just less than 10 lines, all this magically happened, distributed and very, very fast. And very intuitively to read, right? Well, I really love it. I don't know why I don't get this impression from you now.
Which of these lines ran in parallel?
Okay. This method runs parallel by all the workers which store each chunk of the data. When you call the for each on the lines RDD from the driver program, it calls all the workers, which are all the nodes who store their relevant part of the data, to perform this one. The thing about the accumulator is that it is common to all the workers, as opposed to the RDD, where they store only their relative part. So now you can think and understand why it should be associative and commutative, because you don't know in which order the sum and the count will arrive to the main place, right? Okay, so what you can see here, here you just sum it, and it happens in the workers. That is why it is parallel. And here, when you access it by value. And this is performed actually not parallel, but in the driver main program. Okay, you see the value. Okay, next we want to fill the missing values. So we continue with our computation graph construction. We do lines, slice data, and then again, one more list map processing with fill missing values. We go over each value inside each line, and if there is a none, we just assign it with the correct feature min. Another interesting thing to PySpark is that the models, when they, just a minute, pay attention, this is the labeled point structure, which should be fed into the training algorithm. Well, the interesting, or not interesting, it's actually annoying part of training, that the classes should be encoded from 0 to n-1 classes number. So what I do here at the top of the slide is that I encode the class's actual values to 0 to 17, and from what it was previously in the CSV file itself. Okay? So let's look at the computation graph that just was run here. First, you have the data structure. You go and you slice the data, then you fill the missing values, and at some point you just run the graph, and all of the composed functions here, which operate on the distributedly stored CSV, are executed. Well, finally, let's build the models. The models we're going to build are the 3-1. There are much more. Gradient boosted trees are also supported. Even neural networks are supported. I don't see the exact benefits of these models, so we'll omit them now. Well, the first and the simplest, as simple as that, you just run naive-based training. That's it. After this line, we have the trained model, which was trained distributedly. Each node counted its occurrences with the naive assumption, and the model was combined. The second lines, the first one makes the predictions, and the second one computes the errors. Well, it's pretty straightforward. First, you predict only on the features and not on the label. And the second one, you filter out those elements that were not predicted correctly and divide it by the number of complete test set, and you get the error.
You don't have a score function?
Sorry?
You don't have a built-in score function?
I think I didn't understand what you just asked.
You don't have a score function that could do it for you?
Well, when I played with it and I tried, that's what I done. So.
No, I'm just asking maybe because I use scikit-learn and I use it all the time. The score function, which is not.
Okay.
But I'm lazy.
Okay, so what is again what is interesting here is that test, map, and predict are also distributed. Imagine the test is very, very large, and it's stored by I don't know how many different nodes of workers, and it's also computed and predicted. And this one just to make it float, nothing else. Okay, my favorite, random forest. Well, it's as you see, it have quite impressive hyperparameters interface. Actually, there are even more hyperparameters that you can tune in the random forest. But basically, of course, you can you must say the number of classes. You have to specify explicitly the number of trees. You have to specify the criterion according to which the split is computed, whether is it Gini or entropy. You can also set to the classifier the strategy of how much features are used in the randomization. If it's auto, by the way, it is the square root of the number of features for each tree. And the rest is exactly the same as in the naive base. By the way, there is also you can also set the number of bins, which is to how many bins you can divide the values of the features when you're building the trees in the forest.
It's just like the scikit-learn format for the random trees.
I think it is. But okay, so.
Yeah, but the same format. This is exactly.
Okay, so I'm finished. Yes.
In random forests, since it's random, you basically gonna have a different outcome each time you run the algorithm. So can you use some fixed type of data to be able to compare results?
Well,
since you're using random algorithm.
Yes, but well, as I think of it, it actually have two points where the algorithm is randomized. The first one is in the samples, and the second in the features. And we do want to exploit the fact that the data is distributed for building parallelly, in a parallel way, all the trees that participate in the forest. So I love it that it is distributed. I don't know whether it has a seed. I just don't know. But
If it uses scikit-learn, it has a seed.
well, go ahead and try to run scikit-learn on 10 terabytes of CSV file.
But I guess it's the same.
Probably it is.
Same stuff, I guess.
Probably it is. I really tell you that I tried several times, and performance was almost the same between different runs. So I didn't, maybe the model itself was not the same, right? But I don't know. Well, about logistic regression, you're right. It was created by the nature to deal with binary classification, and it exploits one versus all strategy. So once we wrote here that the number of classes is 18, actually we ask behind the scenes for Spark, we're asking it to build 17 classifiers, 17 binary classifiers, each time one class versus all the rest. And basically the prediction and the error computation is the same. Okay, so just to convince you that how easy it is, let's see the notebook we just used in this example. TTT. Did I close it? No. Okay, so here is the code. I just wrote lately what we have just seen in the same workspace on Databricks. You can get it, by the way, completely free. These are my files, so it's really easy. By the way, before we finish, I want to show something else. You can also install Spark without distributed way in your own favorite machine, and just that's the code we just saw was the word count, right? You can just run it, runs beautifully. Also on, when it is not distributed, also distributed process is now emulated behind, just on my computer. We get all the counts for files, so you see it's really simple and very easy. The only difference is that the Spark context, which distributes the work between the nodes, here must be explicitly specified. And on Databricks, you get it, the real one, which is not a fake news, but a real distributor. Okay, so first, all the code that we have just seen present on my GitHub account. You are more than welcome to go and see it. In addition to PAMAP dataset, I have implemented there the training of glove word embeddings, if you know what it is, and some co-clustering algorithm of item to user for a recommendation system, so you're more than welcome to see and use it. Well, I hope I did manage to convince you that it's really, really easy and very fast. And when people I talk to about Spark and Hadoop, and they hear Hadoop cluster, it's a hell, how can we even start with it? So no, it's really easy. Just go and do it, quick and dirty, to make something work before it goes to production, just to learn and play with it, very simple. Another tool that I tried, and I decided to put it here because it also has a built-in notebook mechanism called Zeppelin, which is ultra cool and very easy, is the Hortonworks. They have a Hadoop image with very good support for Mac with a VirtualBox, and with a VMware for CentOS. Works beautifully. Last thing I want to tell you is that Spark and PySpark especially, well, that's like all the things in Python. It's very easy to code it. It's very hard to maintain. The administration, once you go to production and not to implement of algorithm, is an actual profession. Hadoop and Spark have really many add-ons. They have an entire ecosystem, which sometimes is very tempting, for example, the HBase. But if you consider to put it in a production system, which have to be in a very high uptime, be careful. Some of them are real beasts, like the Hadoop itself. What we've seen today was an MLlib library for machine learning, which operates with lists in a lazy computation graphs mode. Actually, there is, from a year ago or something like this, the ML library, instead of MLlib, which is supported by Spark. The thing about it, that it operates in data frames, which are actually CSVs, like tables which are read into the Spark mechanism. And those of you who are more familiar with this kind of work and with SQL, more than welcome to go and try it. And something I also learned in the hard way, when you have lots of text that you need to process and to put in production, don't rush to Hadoop and to Spark. Do yourself a favor and consider other distributed mechanisms which are scalable. For example, Solr or Elasticsearch. They work beautifully, even if you have not only unstructured text, but also text which is partially structured with lots of fields. It works well for many cases. No, that's it. That was the last sentence. So, questions?
Is there a reason why you use in range and not in enumerate? Or
Sorry?
is there a reason why you use in range and not in enumerate?
Just personal preference.
Okay.
More questions, that's fine, because we have another lecture.
Okay, thank you.